Hello, everyone, and I'm excited to be here today to talk to you about ENGR 221 dynamics. So before we start to get into all of the fascinating and the cool world of essentially dynamics, and you're going to learn a lot about different systems, looking at kinetic energy and potential energy, and basically looking at moving systems, we want to have a solid understanding of statics concepts. So you're going to work and you're going to deal with Newton's second law, but we need to kind of have that solid foundation of statics in order to build into dynamics. So that's kind of the critical aspect of what we're going to be doing here today. So specifically, we're going to look at forces, resultants, and essentially systems of forces. Specifically, we're going to focus on friction. And we're going to look at dry friction, or Coulombic friction, and we're going to focus on systems where we need to take this into account. So typically, if you remember, when you start off in statics, you look at smooth surfaces where we can ignore friction. But most of the time, a lot of physical systems, we have to account for friction. So we're going to get into that today. But before we get started, let's go ahead and let's review some of Newton's laws. So first law, what does first law state? If a body is at rest or moving at a constant velocity in a straight line, it will remain at rest or moving in a straight line, constant velocity, unless we're acted upon by another force. Second law, again, for today's lecture, everything that you do in dynamics, yes, second law is going to be very important, but today we're not going to even touch that one. Now, the third law is essentially the law of action and reaction. So when two bodies interact, so if I have body A here, body 1, 2, they apply force to one another. So if 1 is here, then 2 here, they are, again, equal in magnitude, but opposite in direction, excuse me. So for statics, for this lecture today in particular, the first and third laws are going to be really, really critical and very, very important. And one of the most important things that we're going to go over and over and over and over again today is we're going to write down these static equilibrium expressions. So specifically, we're always going to be working with the sum of the forces and the sum of the moments must be equal to 0. And that is going to essentially be how we're going to interpret our first and third law. Now, before and as we start to kind of get into solving problems, one of the important things is that we all are working with a consistent notation and coordinate system. So the one I pick, typically when I'm working, especially with 2D problems, I want my x direction to look like this, my y direction to be here. So this will be, in this direction here will be my positive x, my positive y. Obviously, if they go in the opposite direction, negative. And we are going to always assume that counterclockwise rotation, that is going to be positive. So obviously, that's going to be very, very critical once we get into moments and forces. So additionally, we may remember that moment is going to be equal to basically a distance times my magnitude of the force. So obviously, we have more complex definitions of moments, basically your lever arm crossed with your force. Remember, force is a first-rank tensor property. It is a vector, so it has a direction and a magnitude. But when I'm calculating moment, especially for a lot of these 2D problems, we're just going to be looking at the magnitude of the force times the distance of my lever arm. And remember, so if I have, let's say I have a system here, let's say our good old cantilever beam system, perhaps. And let's just say I've got a force acting here, and I want to calculate the moment about this point O. So if I want to calculate the moment across this point O, remember, I want to look at, there's a line of action, and I'm going to draw this blue here, just to kind of, hopefully this is a good review. Line of action is tangent to the direction of the force. So this is my line of action. My distance is going to be the perpendicular distance, or my lever arm, D, this is going to be the distance that I plug into this expression here. So I could call this like D1. So I'm going to plug in D1 right here. The magnitude of my force will be essentially P here. But it is the perpendicular line of action, my origin. My lever arm is essentially the perpendicular distance to that line of action. So we're perpendicular here. So that is essentially how we're going to calculate moments. Now, obviously here, whereas if I am looking at this origin here, where's the moment, or will it be clockwise or counterclockwise? So we're going to go, and you could do right hand rule. So actually I could put my thumb out of the board and I can see, will it lead to that, or will it curl around the direction of that force? No, actually it's going to be in the opposite direction. And you can see if I'm looking at this origin, we're going to go clockwise. So that will be a negative moment. But anyways, we'll come back to that a little bit later when we start to solve problems. But consistent coordinate system is very, very critical here. So again, for my notation, I am going to use this consistently throughout the rest of this lecture. Now, you can choose something completely different. As long as you indicate that on the page and you're consistent, we're going to achieve essentially the same answer, but it just may look a little bit different or flip direction. So do whatever you need to do to solve the problem efficiently, correctly, and as long as you note that in your solution so that you can communicate that to others, that's kind of the key thing of what we want to do and what we want to learn here. Now, before we get into types of friction, I want to also talk about some critical idealizations, and assumptions that we're going to use in statics problems. So there's three critical ones that we should be familiar with, and hopefully this is just a reminder. So our particle assumption, particles have mass, but we effectively ignore the geometry. Rigid body, this is very important. So we know, or if you're a material scientist, when I apply a force, or effectively a stress, there's going to be some strain to this system. So there's going to be deformation to the material. So in statics, we are going to assume that our body is rigid. So there's no deformation whatsoever, either elastic or plastic, of that body. So it is completely rigid. So this system breaks down. So that's going to be another critical assumption that we are going to make. And finally, we are going to concentrate forces at a singular point. So obviously there are some forces that are not really at a single point. They could be distributed again, but we're going to concentrate them at a single force here, or if we think about weight at your centroid, so weight applied at a single concentrated point. So it is localized at this single point. So hopefully that's a little bit of a review of your statics courses, and now we're going to get into how are we going to deal with friction, specifically dry or Coulomb friction, or Coulombic friction, and then we're going to start to attack some problems. So I'll see you in the next video, and hopefully everyone's excited. I'm excited to be able to give this lecture to you, and hopefully this is helpful later on. Anyways, have a good one. I'll see you in the next video. Thanks. Bye.